I'm not sure what to add beyond what was already what we already said in the last. I don't know which. I guess it was so all the videos have been posted of all the lectures. It was like the end of the first part of the last lecture where we went over this. I think right before the break. And problem one was, I think you can do it just using the algorithm that we use to create that first block column in that whole recursive green function algorithm. Chapter 4, it was like the last part of that algorithm. All right, that's where we actually constructed some off diagonal blocks of the green function. And here's the summary of all the equations, right? So this is here, you're actually creating off diagonal blocks of the green function. And in your ideal chain, you're doing this now for an ideal chain where you're right at every site. You're right connected and left connected. So, looking at this equation, you can probably use it going either way for an arbitrary, replacing 1 by any arbitrary index. Say I, starting from GII, which you know from homework 1, and going either way, left or right. Here we're going, I don't know, think of 1 as being the index I, so here, which way are we going? We're going, moving this index to the right, right? So you're relating j to j minus 1. So you're moving this index to the right. And to move it to the left, we'd probably just have to replace this with the left-connected green function, I'm guessing. And then you just need to play around with it. I mean, that's the whole point, to see what it's like to play around with recursive green function algorithm. Try out some stuff. And you know the answer, right? The answer is given in the exact solution is given in sort of a section in chapter 1. We write down the exact form of the Gij for the infinite chain. It's basically, I think, just looks like GII times e to the I Ka magnitude of I minus j. So you'll find that in one of the latter sections of chapter 1. I think in chapter 1, we just wrote down the solution and showed that it was true. So now you can actually derive it from this recursive green function algorithm. So basically, problem 1, you're going to play around with what we're doing here. This is the only place we created an off diagonal, use RGF to create an off diagonal element of the green function. Starting with the diagonal here, then recursively generate all the off-diagonal elements. That's the idea. Oh yeah, and then this one, again, I'm just kind of repeating myself from last time. Problem 2 is you're just this is an exercise and give you some intuition about these generalized boundary conditions where you don't have a lead anymore. Your left lead is now just a single site with an imaginary term on it. And you'll see that nevertheless, you get a perfectly finite transmission, and the shape of the transmission is going to strongly depend on that value of the imaginary potential you put in on that left site. That's all that's doing. And it's really easy. I mean, actually, it makes, in terms of the math a little bit easier, because your surface green function is just 1 over e minus epsilon plus I eta, and I think we're saying epsilon is 0, so it's just, as I wrote down here, it's just that's it. That's your surface green function at site 0. And so you use that expression in your self-energy from the left lead. That would be, T squared times this is the self-energy due to the left lead. Right, T squared times, and what's the coupling element? Is it just, so what am I doing here? So we're treating the right lead in the wideband limit, so it's just some gamma r, which is fixed, I guess, 1 MeV. And then this TL is 10 MeV. So TR never enters into the problem since you're just replacing it with a known gamma r. But TL is used for the left self-energy, and your left self-energy will just be this TL squared times this thing. That's your left self-energy. And the imaginary part is your left gamma, or -2 imaginary part is your left gamma. So the sigma on the left is just TL squared times over divided by this E plus I eta. Right, that's the self-energy on the left. And then gamma L is the usual. Gamma L is just the usual -2 imaginary. That's always true. Sigma L. So you got your, and you're given sigma for the right. And which structure are we talking about? What's figure 2.6? Anyone remember? Is that the, oh, that's the resonant, that's the one you just did for homework 2. Right? That's the one where you've got that one, central site, which is our resonant level, and then you've got, we had an infinite chain over here. But now we just have one site on the left. Right? That's the one you just did for homework 2. So, so the green function is still same as it always is. E, I'll write out epsilon, but epsilon is 0. E minus epsilon minus sigma L minus sigma R inverse. That's what it always is, right? That's your green function. So that equals, so that's your green function for the device. And then, so you've got your green function, your gamma, and then your transmission, please everybody, is gamma left, gamma right, times your green function, since it's just, everything's a scalar, times your green function squared. Magnitude squared. Magnitude. So your transmission's a real quantity. And that's it. And then you just play with some parameters and plot t. You play with the value of eta and see and plot t and see what t looks like as a function of eta. I think that's all you're doing. And let's see, for a current, derive an expression for the current as a function of eta. So let me change that. Current, I don't think I want to say current. I want to say transmission. Because current depends on F left and F right and all that stuff. So forget current, just say transmission, which is what you're going to plot anyway. Right? You need to do this anyway to finish the problem. You just want to derive an expression for the transmission coefficient as a function of eta, which you need to do anyway to finish off the problem. So, okay, everyone made that correction? All right. Correction noted. So that's pretty straightforward. I mean, everything, these are all the pieces you need. Just put them together, stick it in the MATLAB, and plot it out. Number 3 is my favorite problem. So you got those notes, because I think I'm going to kill them now. They're going to disappear. I need the space. Everyone got this? So here's the one, I guess we just have the ideal chain that we've done ad nauseum. And we just are connecting a node to site, I don't know, 1 or 0 or something. I guess to site 1. So at site 1, we're attaching a node, this extra node, with some coupling, I guess, what are we calling it? Some coupling TR again. And we're calling this node R, I guess with an energy epsilon R. And again, we're setting all these energies equal to 0 on the chain. And So then you know G11 of the chain, so you want to get G11 of the whole system using Dyson's equation for A. And I'm sure this will just, don't really have much to add than what we said last time. Right? Your bare system is this ideal chain, and your isolated site with no coupling in between. That's your bare system. So any green functions, bare green functions, have got to be for that system. So the bare green functions on the chain will be the exact green functions of that chain. So the bare green function of the chain, G11, is the exact green function of that infinite wire. And the bare green function of the isolated site is just 1 over E minus epsilon r, just the green function of the isolated site. And so once you get the exact green G11, you're focusing on G11 because that's all you need to get transmission. Because the transmission, the only thing that's coupling to the leads is 1. Site R is not coupling to the leads. Site R is not coupling to the leads. Once we hook all this together, right? Your system looks like let's see if I can do this. It looks like you have your left lead, you have your right lead, and then your device is this thing in the middle. So here's your device, and the only coupling between the leads and the device is to site 1. Right? There's no coupling to site R between the leads and the device. And so that's why you got this. I need more space here. You good? Let's make this disappear. And so that's why if I were to write the 2x2, sort of the E minus H minus sigma for the device, that's going to be a 2x2 matrix because there's 2 nodes in the device, right? But only node 1 couples to the lead, so it would be E minus epsilon minus sigma left minus sigma right for the 1,1 element, and then 1 couples to node R with TR, TR, and this would be just like E minus epsilon R. Inverse. So that's the green function of the device. This thing is the green function, the full green function, right? The device is two nodes, so it would be a 2x2. This is G I J, where I and J are either 1 or R, the way in my labeling system. Site 1 or site R, that extra site I stuck up there. So that is the green function, right? The inverse of this matrix, right? The inverse of this matrix. And so with this, you can easily check your answer. So, I want you to use the recursive green function. This is the whole, chapter was about RGF. So this is a good exercise in using it. But with this, you can you can check your answer because, the inverse of the 2x2 matrix, you switch the diagonals and take the negative of the off diagonals, right? So the 1,1 element of the inverse is going to have E minus epsilon R in the numerator, divided by the determinant, right? Which is just going to be E minus epsilon R times this, E minus epsilon minus sigma left minus sigma right minus T squared. That's in your denominator. That's the green function of this is the 1,1 element of the green. This thing here is G11, which is what you're after. Right? That's what you're supposed to get using the recursive green function algorithm, and you're going to have to write out explicitly what the sigma L and sigma R are. Right? I mean, sigma R is easy. That was your negative I gamma over left over or right over 2. Sigma left is that other thing, which, so sigma left was your t squared over E minus epsilon R, right? That was sigma left. Is that right? No. What was sigma left? Oh no, that was the other problem. Sorry, my bad. You got to check what I say in these discussions. I start going too fast. Sigma left is the same as sigma right. Oh, they're the same thing. Are we using the wideband approximation here? Does anyone have a copy of the problem? Are we supposed to use the wideband? I think we're supposed to use the wideband approximation. Just so both sigma left and sigma right will be like sigma, or negative I gamma left or negative I gamma right over 2. Yeah, that's the first sentence of use the wideband approximation. Starting with that, calculate G11 in this using Dyson's equation, the exact G11. And then in B, use the wideband approximation. Determine the zeros and poles. So, okay, in the wideband approximation, sigma L is just, you know, negative, what is it? Negative I gamma L over 2. Sigma R is negative I gamma R over 2. And then I say find the zeros and poles of this thing. So you got to multiply, so, you know, these two terms together will just become plus I, you know, gamma L plus gamma R over 2, which is I gamma over 2. So that'll be the imaginary term. So you're going to have finally the denominator. You're going to have, you know, E minus epsilon R over E minus epsilon R times E minus epsilon, which we're setting to 0, plus I gamma over 2 minus TR squared. So you got to you know, multiply that out, solve the quadratic equation, find the 2 zeros of the denominator, and those are your poles. I think I say in the question to do that, because, you know, when you do the quadratic equation, you're going to get the square root of something. And I say then approximate something as being small, like TR is TR. This coupling, we're assuming it's weakly coupled, is much less than gamma, because gamma is the gamma of that infinite chain, so it's like your bandwidth. It's something on the order of the bandwidth, the gamma for just the ideal chain. So then you then evaluate something in the square root using, you know, the square root of 1 plus x is like, you know, 1 plus 1/2 x for small x. So you can get a nice clean expression for the zeros of the denominator, which are the poles, right? So the 0 is, I mean, when this green function here is 0, it's going to be 0 when E equals ER, right? There's your 0 right there. When the numerator goes to 0, that's easy. And you'll see when the denominator is going to go to 0 when it's going to have a pole close to ER. So you're going to have a pole that's very close to that 0, but a little bit shifted. And then another pole that just corresponds to what you would get from that semi-infinite chain. So you see the semi-infinite chain, you see that sort of isolated site, and you see that they're both shifted a little bit due to their interaction. And finally, I guess, I don't know what's the rest of the question. Let me see the question again. Thank you. So you sketch the position of the zeros and poles in the complex plane. What's the transmission when, so when E is exactly equal to, and well, this is going to tell you, when E is equal to ER, the transmission, since it's proportional to G squared, is going to be 0, exactly when the energy is aligned with the energy of that isolated site. And then I say, okay, now, and so everyone, let me go back, because some people, like, I'm kind of going back and forth, so let me highlight this in red. So D, for D, using the exact expressions for the lead self-energy, so no longer wideband approximation. You know, but the exact expressions are easy. They're like, you know, I don't know, e to the IKA over T or something, right? What we did from chapter 1. Or you'll have to need them in terms of energy, which we also did from homework 1. So now using the exact expressions for the lead self-energies, and the specific value for T and TR, epsilon is 0, epsilon R is -1 eV. So I think the way I've set this up with these parameters, I'm aligning ER. ER is aligned here in the lower half of the band. So this would be like the top of your tight binding band. This is the bottom of the tight binding band. And this is the middle, so this is ER, like a quarter of the way up the tight binding band, the way I've set up these parameters, at -1. Because this is 0, your epsilon is 0, and your band goes from, you know, -2T to 2T, or whatever, the bandwidth. And so we already evaluated it, right, edge, when the energy was, let's see, what are we doing here? So, okay, now plot T. Oh, T is a function of E. So you're going to plot T of E for some energy range around ER. And then I say repeat for ER exactly right in the middle of the band for the next part E. And as I said before, you should see something, I can't remember whether the peak or the 0 comes first. Because the 0 is very next to the pole. So here's the 0 when, you know, right at ER down here, and then the pole is very close to it. So you get this feature here that's called a phaneresonance. And this is a very classic problem in physics where you have what do they call it? A localized state weakly coupled to the continuum. So it's our localized state, epsilon r, and it's weakly coupled to that continuum of states, i.e. that band of states from your infinite chain. A localized state weakly coupled to the continuum. It shows up in optics, and this is how what problem Fano was working on. It shows up in like some localized D state weakly coupled to some band of states, and you always get this kind of shape to the transmission. And the physics behind it is I mean, one way to think about it is constructive and destructive interference. This shows up in systems where you have, you know, 2 paths to get from A to B. Here's one path, and here's the other path, and they constructively or destructively interfere. So in systems like this, you end up seeing these phaneresonances. Another system that we saw it in was the tunneling through this system here, a gallium arsenide, aluminum arsenide, with an aluminum arsenide barrier. And so this is the gamma valley for the conduction band of gallium arsenide. And aluminum arsenide, the gamma valley sits up here, but the X valley sits down here. So it's actually an indirect gap material. And so the electrons in the gallium arsenide are all sitting happily at gamma. But suddenly there's two paths to go from here to here. One, they can just go gamma, 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 in which case they're evanescently tunneling through the evanescent gamma state, or they can go gamma X gamma and go through the real X state. And that gives rise to this phaneroresonance. And so in terms of the X value, this X state here is really a bound state, because in gallium arsenide, the X state is up here. So this X state of the aluminum arsenide is really a bound state weakly coupled to the continuum of the gamma states in the gallium arsenide. Okay, so that's physics. And that's the hour. Well, we started late. So any questions? Okay, so we said this time you would come with some work that we could check to see if you were on the right track. Questions? Comments?
Is there a minus sign in front of equation 1.12?
Equation, which one?
So here in the problem 4.1,
yeah.
The first problem you have told.
Yeah, there's a minus. There should be a minus sign. I actually went back and corrected that. It's like I keep finding these, because I went through the same thing myself. I went back and looked and said, wait, it's there now.
For number 1, we can use the recalculation of capital G J1 to find all the columns. J1, yeah, first column, and then we also need other elements. But for that, I need one left-connected equation. But I cannot find a left-connected equation, so that we can find all the rows of the.
Oh yeah, the rows, right, yeah. Right. Well, we had one for the column, right?
Yeah.
But since this problem says just a simple ideal chain, so we can take any point, and for that point we can just calculate the first column. And since the chain is ideal,
so that one can be an R, but then if you start at the first column, all you get are indices greater than 1, right? You only get, like, if you think of ij, you get all the answers for j greater than 1, j greater than I, using the algorithm we wrote down, right? You don't get the answers for j less than I using that algorithm. So using this equation here you're talking about, yeah? 4.46, and that gives you everything, let's see, for j greater than 1, right? J an element of 2, 3 through n there. It doesn't give you values for j less than 1. So does anyone have any ideas? Anyone made any headway on this?
There is general equation of capital G I J. I was thinking whether we have to derive similar way for column vectors.
Yeah, you do.
We have to.
Yeah.
but the thing I don't understand, since my system here is symmetric, do I need to go through all the calculations? I can just take one point, and for that one point I can just calculate all the columns, and that should be the same for any point.
It should be, but I'm asking you to show that using the recursive green function algorithm.
Right, but do I need to just show that? Because if I want to just check it against equation 1.142,
yeah,
then just take any point, and for that point just calculate all the columns of the Green's function. But that point is arbitrary, so I can move that point to the right, and I can also move that point to the left.
Okay, but if you move it to the right, this algorithm does not give you, so let 1 become the number 2, and 4.46.
No, I don't need to go through actually this algorithm, because when I choose that particular point, that was arbitrary, right? I could have chosen its left point or its
Give me a number. Which one, if you want to replace 1 by some other number, just to be specific so we can talk about, otherwise it's too abstract.
Okay.
Would you like 1 to become 2?
Okay, yeah.
2. Okay. Then
Yeah.
what is, using this, does this formula work to give you G12 for J equal to 1? In other words, J is, if you think of the indices as GJI, now J is less than I. And will this algorithm work? Is this Dyson equation correct? That's the problem. You always have to draw a picture. So now we have site two, and that means we're going to, this is sort of our, becomes our V, T12 and T21. And so I'm breaking my unperturbed system are these two uncoupled semi-infinite regions, and I have I know the diagonal elements, the exact diagonal element, and I know the right and left connected green functions. They're going to be the exact green functions of the unperturbed system, the one I drew here. So if I have, what do I want? I want G12, I guess, right? That's what I'm looking for. And so, what would I have? I would have that's equal to whatever it is I start with. I have to start with the index 1, right? This is why the indices are so powerful. So I need something that starts with an index 1, and the only thing that starts with an index 1 would be a left-connected green function, right? T12, and then the exact G22. I guess that's the only difference, right? That's it.
Yeah, that's the equation we need. But did you actually mention this equation in the text, or it's?
Well, it looks just like 4.46, right? Except I changed the little triangle from right to left. I mean, it's the bare one on site 1, and the only bare one on site 1 is your left-connected green function, your coupling element, and the exact one on site 2. That's the only terms that come into play. Now, a more interesting question is, assume you only know this, that you've only calculated this. Then what do you do?
But left and right connected, they're the same.
That is true for an infinite lead. So let's assume it's not an ideal lead. Then this equation is still correct. Let's assume they're different. And the only thing you have to work, is that you've calculated and stored away is, say, your right connected one. Then what do you do? Any ideas? I mean, if you're modeling a nanowire, each one of these can be a huge block to store away. You don't want to have to store away both. So if you can figure out how to do this just using one of them, you're far better off.
Then I can derive something like equation 4.45, right?
4.45.
Yeah, I have only the right connected ones.
Yeah, but that's for the diagonal. Although there is something about 4, 4, 4 and 4, 4, 5 that is relevant here. And the way we derive those two. If we go back and look how we actually derive those. We use two different equations. And this looks kind of like the one we're looking for, actually. And that's exactly why we did it like that. So you didn't have to store away both left connected and right connected green functions, because it's very costly and expensive to do that. First you have to calculate them, then you got to store them. So both storage doubles your calculation, doubles your storage. Right, this is the alternate form of Dyson's equation. There are two ways to write it. One was like, you know, a little, in general, G plus, this is the normal way you see it, and the other way is G plus G, be little g. So it looks like you got all the equations you need for problem 1. So I mean, the only real trick is to show that you get this, you know, this absolute magnitude. Well, it's different from a wave function, where it's, you know, you've got this phase factor as e to the I k, but it only depends on the magnitude of the difference, which is different. And this is actually why when you take the you kind of take this to like a continuum limit, r minus r prime or z minus z prime, and you take the second derivative, you end up with a delta function, right? That's why it's a green function, not a wave function. Because right when the sign of that second derivative will change signs, right, as you go between I and j. Because on one side it's e to the minus I k I minus j, the other is e to the I k I minus j, or for the absolute value, as the sign of I minus j changes. Don't see that? It's not obvious. So if you have I and j, site I and site j, right, over I, j. So over here it's e to the minus I, k, I minus j. And on the other side it's e to the plus I, k, I minus j, right? That's a non-analytic function. Suddenly just changes sign, and that's why you get, if you think in terms of z minus z prime, that's why you get a delta function when I equals j. And the second derivative, d squared dz squared of e to the I k magnitude z minus z prime. And I think that problem number 1 was always the trickiest, although all the equations are already there for the asking. People always have the hardest time with that one. Yeah, it should be easy. I mean, if you just look at the explanation for what's going on the left side, it should be apparent for what's going on the right side.
Isn't the question the same one you discussed in class?
I'm sorry, what's that?
Isn't that you discussed in the class, in the last class?
This one?
Yeah.
Yeah, I did. I mean, I discussed what was going on the left side here, right? And this is about what's going on over here. That if you know, as the band edge starts falling here, if you look very closely, it's hard to see. The band edge starts rising over here. And so I'm just asking you to explain it in the same way we, you know, using these equations, explain what's going on the right side, and sort of following this explanation here. I mean, are there any issues with using Dyson's equation for 3a? We sort of did it using just solving the matrix exactly. I mean, there should be 2 lines to do with Dyson's equation. Well, Dyson's equation can be tricky if you. Has anyone written out Dyson's equation for this?
For 3a?
Yeah, 3a.
I think I've done it.
Did you check to see whether you get the same as just inverting the matrix? I see. Yeah, I mean, at least you know just by inverting the matrix, you know what you should get.